Welcome everyone to our next episode of this exciting new webinar series called EvoInsight. We are thrilled to have you join us here today on this journey and for future episodes. It isn't just about new content, it's about starting new conversations, a new community, and just sharing a whole new wave of insights. And for our next topic, we're excited to share, we are going to be talking a little bit about the pressure of calibration in the aerospace industry, specifically for aerospace. So super excited to let you know who our next guest is. It's going to be our CEO based in the UK, Paul Crowhurst. And he comes with a fascinating background in mechanical and measurements engineering. So a huge range of insight that he's going to be sharing with us today. He'll be answering a few questions, giving us some unique insights in today's session. Grab a coffee, find a comfy seat, and let's dive in. Paul, thank you for being here today.
Absolute pleasure, Lindsay. Thanks for having me on.
Okay, we're going to dive in. So the topic that I've just mentioned is the pressure of precision. And it's kind of covering, we want to cover the common pitfalls in flow measurements, especially in calibration for the aerospace industry. So we're going to be talking a little bit about the pitfalls the engineers don't often talk about. So can I get into the first question with you?
Please do.
Okay, so in your experience, what are the most overlooked sources of error in pressure-based flow measurements, and why do they tend to go unnoticed until later in the testing?
I think one of the things is that majority of the time, people plan their measurement campaigns quite carefully. But the overall measurement chain really needs to be thought about quite hard and carefully in order to bring about good measurement. It's the old adage about if we're not measuring something, we can't improve it. Yeah. So we need to be looking very hard, very carefully about, okay, how do we bring about good measurement? And we've really got to be thinking about the front to the back of the measurement. So if we're thinking about measuring something on an aerodynamic flow surface, for example, fitting our pressure measuring instrument somewhere close to the measurement point and expecting to get good results is not necessarily going to bring us a good result. Yeah. We need to think about how we're capturing the measurement point itself, and there are a number of semantics wrapped around that. How are we transmitting that measurement back to the measuring instrument, and then what are we doing with the signal processing, and how we push that on up the line? So that's a fairly complex group of topics on its own, and quite often there are oversights that are made that could be very easily dealt with. It's one of those things that we offer as a business, is we help people to look at what does the overall measurement chain look like.
Okay, that makes a lot of sense. And would you just, off the top of my head, would you kind of say like environmental factors affect measurements, and also just like sensor drift or the actual setup to go with, would that play a big role in errors?
That's a very astute set of questions that you've got there. And I think one of the things that needs to be remembered is that the physical measuring element that you're using is exactly that. It's a physical, living, breathing thing in some contexts. And we have to create the right environment in which for that to operate. Look at something like a pressure sensor. For example, the biggest source of error on any pressure measurement is its temperature, and it needs accounting for, it needs correcting for. It needs dealing with in the right way. And so there are a number of characteristics that need to be taken care of, considered within that. Vibration, you mentioned, quite often where we're working is in a high vibration environment, and that needs to be provided for. You can't get rid of these effects, you can't get rid of these transients, but you need to be aware of them and have some level of compensations or ways to deal with them within your own measurement circuit. To give you an example, our pressure scanners that we build all go through thermal cycling processes in order to tune out, de-stress, create the environment in which the pressure sensor can really give of its best. We also do a lot of work with vibration testing to ensure that we understand how the sensor is going to behave. quite often we're supplying equipment with vibration dampers fitted to them, so that when they go into the operating environment, they're really going to give of their best. Because what the customer is really interested in is, am I getting a good pressure measurement? In some ways, the temperature part of that, the temperature component, the vibration component is of secondary interest. What they really want to know is that that's not causing a problem with the pressure measurement. So it's important that we do our side as the instrument supplier to make sure we've done our work there to really make that part as easy as possible for the operator.
Sounds good. So it's almost like the whole question kind of sums it up. It's almost like an unseen error for customers. We obviously seen it ourselves because that's what we do in the calibration department. So we are looking out for these particular things. But for them, it's these sort of errors that they're not thinking out loud, or like I said, an unseen error.
Yeah, absolutely. And it's very easy in a lot of situations to make the assumption that because the instrument is giving a measurement or a reading that we don't recognize, that there is a problem with the instrument.
Yeah.
Quite often something that looks like an erroneous measurement is actually the instrument telling you what it's seeing, telling one what it's seeing. And it could be very easy to, in inverted commas, shoot the messenger. Whereas actually it's telling us something about what's going on in the process, and we might need to look very closely at that. And there's all sorts of things that play into that. Height, for example, you go just a few feet up in the air with a pressure sensor and you will get a change in the output pressure from the sensor. And
oh, wow.
In general, we don't think about that. Why on earth, if I climb 2 stories in a building, is my pressure sensor changing? Well, the pressure is actually changing. That's not a fault within the instrument. It's relaying what it's seeing. So it's telling us something important about our process. Again, with the benefit of that kind of knowledge, we can then use that to learn more about our process, learn more about the thing that we are actually measuring, and dial that back into our whole measurement process.
Yeah, very interesting, because I would have never thought that. And a lot of others would never think that. And it's actually almost too smart for its own good that it's calculated in that factor that you've gone up 2 feet versus where you are at level. And it's doing that on behalf of you, which you haven't asked it to do, obviously, but that it's really thinking that for you.
Absolutely. And again, why would you think that? It's in some ways we're expecting that the sensor itself is a dumb animal, but actually it's giving us a really incisive look at what it is that we're trying to measure. And I've had some of those conversations with some very experienced measurement engineers in the past at some very recognizable companies, and we have the tendency to take these things for granted, in that just because we've got an accurate instrument, that it's then giving us an accurate measurement. Again, back to my earlier point, it's really important we think about, are we bringing about the conditions for good measurement? Because if we are, the likelihood is we'll get a good measurement. If we're not, it's the old story about garbage in, garbage out.
Very true. Okay, well, thank you for that. That was very interesting, and I learned a lot just by answering that question. So I'm going to move on to the next. And it's probably going to fall a little bit onto that first question. So how do environmental factors like temperature variation, vibration, pressure fluctuations impact calibration accuracy? And what best practices, in your opinion, do you see and use to mitigate them yourself?
It's a very good question. It's one of those things that a lot of people don't necessarily pay any attention to, and it's something that we as an instrument manufacturer have a responsibility to be able to take care of, so that our clients, our users, don't have to think about that. I made an earlier point about the pressure sensors being a physical living element, and we have to treat them as such. There are no 2 pressure sensors anywhere that will have exactly the same operating characteristics. We build instruments that can have 16 or 32 or even more sensors in one compact environment, and that could be something that's maybe a 50 millimeter square. So it's a very compact environment. It'd be easy to assume that the operating condition in that environment was the same all the way over. It isn't, and the sensors aren't. And I was sat with a group of students a few years ago, having a bit of a conversation with them. and explaining that our role is to make the sensors behave as if they are operating in concert, as if they are of the same physical construct. And some of the sensors that we use are about a millimeter and a half square, so they're extremely small. Some of them can be cut from the same wafer of silicon, and so the physical characteristics are very similar, but when you put the sensor into its actual operating environment, you're changing some of the mechanical characteristics of that, and it has to be dealt with properly. Otherwise, we're not going to be able to bring about a measurement system that will give good quality, repeatable, reliable measurement over time, and that's really important. So we've done, or we do, as other instrument manufacturers do, a lot of work to mechanically, thermally stabilize the measuring instrument so that it's going to give good long-term performance. We apply instruments also to the things like the circuit boards that will apply a local temperature correction and enable the instrument to operate over a wide temperature band. So we can be anywhere from, say, minus 30 degrees C up to 100, 130 degrees C, wide temperature band, but operate in a very linear fashion across that range. We also need to understand how vibration is going to play a part, because it will have something of an impact. We need to look at things like signal to noise ratio of the pressure sensor, so we understand how that's going to go. We spend quite a bit of time putting our pressure sensors onto a vibration shaker table, for example. So we'll apply pressures to the instrument while it's being bounced around on a shaker table to watch what happens. And we can't get rid of the vibration. We can understand the impact it's going to have on the pressure measurement and whether that's likely to be of consequence. If the vibration was so strong that it pushed the pressure sensor outside of its operating specification, that's a problem. Okay. If the signal to noise ratio in the sensor is low enough, it becomes a part of the overall measurement. So by the time we have finished manufacturing an instrument and put it into the hands of the customer, they can be confident that the instrument will operate in their environment over a long period of time and give good service. So we're doing a lot of that front end work to make it easy for the customer to plug the instrument into their process and start getting good quality data from it.
Okay, so you kind of answered my question, because my follow-up question was going to be, do customers give those specifications beforehand? Like, we in a closed environment, this is our temperature, we on this sort of aircraft, so this is where we're going to be calibrating. So you've kind of answered that in the sense that you've covered a wide range of spectrum, so that whether they're in this temperature or that temperature, we kind of have covered it for them. Is that correct? Or do customers ahead of time, do you have that information?
That's another very astute question, Lindsay. And I think one of the things is we do a lot of market research so that we understand the environments that we need to position the products for. Quite often, our clients are not able to give us complete pictures of what's going on in their own processes, because sometimes they don't know. And that's a completely innocent thing. It would be very easy to ask, how can you possibly not know that? But it's a reality of the situation. We're operating on things like single seat race cars, aircraft, where you have big thermal shifts, big vibration situations that need to be paid attention to, and that you're also going to get unforeseen conditions. We've had instruments on racing cars that have got caught in fires, for example, and that's going to put instruments under a stress that we haven't tested for. We don't get, while we do thermal extreme testing, we're not sat, for example, with a blowtorch, seeing if we can cook our instruments. It's an extreme condition we wouldn't ever necessarily expect to see. This said, we have had instruments in that condition where they've been caught in some quite nasty fires. We've had the instrument returned to us, and actually we've been able to get them working again. So they will stand up to far more punishment than we've given them credit for. But again, what we want to do is understand, okay, where does the application sit? What can we do to help with that? To go back to the earlier point about we're bringing about the conditions for good measurement. Talk to us about what do you believe your overall measurement envelope looks like, and how can we help you to achieve the best possible measurement capability? when considering all of those effects, like the temperatures, the vibrations, humidity, even that can have an impact that we don't necessarily always think about.
Yeah.
So a number of contributing factors there.
So basically, excuse the pun, it is literally the pressure of precision. That's our topic today, because there is that you don't know the insights to it. So it is that underlying stress that you just don't know your environment. So it is that the pressure on you to get that precision accurate. And that's where we obviously fall in, because we are taking that away from you to do it ahead of time.
Yeah,
understanding the application, knowing the application, and we figured it out for you, basically.
Yeah, we spend a lot of our time. We have teams across the North America and Europe, and part of our role is to get with the customers, come and see the customers on their own site, have a close look at the application, and make sure we're taking an extremely prescriptive approach in what we're doing. And quite often we will look at something and say, there's going to be a problem right over here unless we pay attention to that. We very rarely just supply a piece of equipment without having some level of detailed conversation to understand the customer's application. They're all different. You can have two applications with two businesses that look the same, two applications that look exactly the same, and you can end up going in very different directions, because the use case or the perceived requirement from the customer side can be extremely different. So it's really important that we pay a lot of attention to that. Again, what we want to see is that the customer's getting good use, good value, and getting good measurement, because that's going to tell them then far more about their process and their application, and add a lot of value to their own business, to their own product where they're doing product development and those kinds of things.
Okay, absolutely. Okay, so question 3. We are going to cover a little bit more into the calibration process. So where in that process do you see the biggest breakdowns, and how can teams improve the confidence in their measurement results?
That's a good and big question, because people can have a varying perception of what calibration means. In general, with a calibration, you're going to take something to a reference standard where you're going to take a series of measurements against it. That's generally a controlled environment, pressure inside the test area, the ambient temperature, humidity levels, those kinds of things. Then the instruments that are being used to make the reference measurements. Am I using a pressure standard, a temperature standard, a source of accurate temperature measurement for the instrument under test? All of those different things need to play a part, and you'll come up with things like uncertainty budgets and those kinds of things. So that in itself is a whole area of study and of expertise. Get out into the field. You've got a racing car over your shoulder there in the picture behind you. When you're on track, you're into a different environment, and there I'm looking at something like a validation. I want to understand that my instrument is behaving in the way that I expect it to. So what can I do? I turn it on, it starts shooting out a measurement. Can I be sure that that's accurate? And giving me the detail that I need. It would be very easy to bring a portable pressure standard or reference to the location, put it next to the car. I've got broad agreement within a few fractions of a percent, so I'm confident that I'm going to be able to take some good measurement here. And what happens if I've got an offset? All instruments drift because they have physical characteristics. So it might be, and this is a bit like zeroing your weighing scale at home. You're getting ready to make a cake or something. You turn the scale on, and you've got it's somewhere away from the zero. So the first thing you do is you bring it back to zero, and then you start your measurement from there. You're weighing your ingredients. It's the same thing with a measuring instrument. So we can have a car sat on a line or an aircraft getting ready to take off or something like this. I'm going to zero my measurements before I start. So again, I'm bringing about the condition for good measurement. And it's really important that those checks that you're doing, or the one is doing, are proportionate to the environment that you're in. So you could be doing a whole load of things that are not relevant. Don't necessarily need to be looking at those. It's got to be they're proportionate to the environment that you're in. Again, it's something that we can advise on. We have a lot of high-end measurement, but also high-end metrology and calibration expertise within our team. So we're able to help with that. Very happy to do so. But it's got to be proportionate to what's going on in the local environment.
Okay, so there's a lot of human factor in that process, And once that human factor is, well, obviously understands the process, then it's going about the actual calibration procedure, because you've got to make sure the environment's correct, the humidity is correct, the vibration wherever the surface is correct. So there's a lot of human factor involved beforehand, which could lead to errors if the human factor isn't obviously understanding the process correctly. Am I right in saying that?
You are. And in some environments, we have seen the human factor be a bigger contributor to a measurement inaccuracy than anything else that's in the process. And you know, we continue to learn. Measurement technology, measurement disciplines continue to evolve. We're still very much on the journey with this, despite how far technology has moved. And we have seen, you know, one of the attributes of our business, one of our capabilities is that we can build automated test, measurement, calibration systems for various environments: aerospace, automotive, defense, instrument manufacturing, calibration, those kinds of environments. And in some of those, we have almost completely eradicated the human intervention and been able to bring about substantial improvements in the overall measurement capability of the calibration system, that has then gone on to improve the operating capability of our customers' own instruments. Because when you automate at that level, when you take out the human factor, when you put everything on the ability of an automated instrument's ability to produce, obviously using the right kinds of instruments, you can really dial out quite a lot of human factor and bring about much improved measurement performance. So human factor is important. You can't ever eradicate it. It's something we have to pay attention to, but we've also got to be able to recognize what looks good and what doesn't look good. We learn to recognize what's normal by seeing what's abnormal in a lot of ways. So yeah, we need to make sure we're paying attention to those things.
Yeah, because you know ahead of time the instrument itself, the accuracy is there. You trust in the instrument to do that job for you, because you've got the accuracy, you've got the measurements in place. So yeah, it is the human factor to just trust your instrument.
It's an assumption to pull an instrument out of a box and assume that it's working correctly straight off the bat.
Okay.
So it's really important, and this is one of the things that we're very careful about. We want to make sure that our customers are going to get good value from their equipment from the moment they get it. And so we're quite often, unless it's somebody that's long established with us, that we know that they're 100% confident and competent with the equipment, quite often we're supplying a lot, or providing with the supply a lot of support to make sure that the customer is going to be able to get some best practices in there and get the best use out of the equipment, so that they become confident and competent with the instruments as soon as they possibly can.
Well, I'm learning so much today in this session. Okay, so the last question, you touched a little bit now in the end of that sentence. It might be controversial, because the question is good enough calibration ever acceptable in aerospace testing? Or is that mindset where most problems begin?
It's a big and challenging question in a lot of ways, because it really depends on the environment. In something like the flight test world, you can't leave anything open to chance. No. You have to be making sure that all of your equipment is of the highest integrity. It's going to be able to give off its best, the measurement configuration, because cycling right back to the beginning, the measurement configuration is very well put together. We're dealing with flight safety here, so it's extremely important. So margins for error are extremely thin, close to zero. We can't afford those kinds of things.
Yeah.
Get into something like a bench test on a component, for example, the risks are mitigated, the risks are significantly lower. So there's an element there of what's proportionate to that particular test. Equally, you wouldn't bring about something like a sledgehammer to crack a nut. So you wouldn't apply the same disciplines necessarily to a flight test that you'd use as a flight test process to something you're going to do on a bench. Again, it needs to be proportionate to the type of measurement that you're doing. And again, it's something that we can and do help with is find out what's proportional and proportionate to the testing that needs to be done.
Okay, so overall, I mean, when I was reading that question, overall, because it's in the aerospace, good is not enough, especially in that aerospace industry. Like, you have to have accuracy, 100%, I would think.
Absolutely. I mean, we get involved with it at multiple different levels. We're dealing with clients in the engine development and test environments. We're dealing with airframe development, all kind of pre-flight or pre-aircraft launch. Once we've got beyond that point, we do a lot of work on in-flight testing, avionics test and verification and calibration. And aerospace is the most heavily regulated environment anywhere in the world. Pharmaceuticals have a high level of regulation. Aerospace is even higher because in a lot of ways the risk factors are pretty extreme, and factors of safety tend to be, relatively speaking, quite thin. But the level of regulation is very high. Aircraft need to be tested for their electronics, their RF, radio frequency level avionics on a routine basis. Altimeters, airspeed indicators all need to be tested on a regular basis. Pre-aircraft launch flight testing, again, very heavily regulated. We've seen a number of air crashes just recently, some tragic stuff going on right at the moment. That's heart-wrenching, heart-rending to see, and you can believe the people that are involved with those flights on a daily basis are taking their safety and what they're doing extremely serious. So it's harrowing to see that sort of thing going on, but you can believe that very high levels of discipline are being used in the testing environments to make sure that those aircraft are flight worthy.
Yeah. So with your background in engineering, would you say, off the top of your head, maybe just name two the common pitfalls that engineers don't talk about behind the scenes? Because we obviously wouldn't see that on a day-to-day basis. So as an engineer being in that environment, what would you say are pitfalls?
I think it's understanding your measurement requirement. It's anybody can take a measuring instrument and attach it to a process and assume that what you're seeing is good data.
Okay.
And attention needs to be paid to make sure that you're bringing about the conditions for good measurement. And quite often and it's an experienced eye that can help with that. Quite often there are things that can be done to help that. Again, just circling back to the picture that's over your shoulder there, we do a lot of work in aerodynamic development for all sorts of industries, and even fitting something to the aerodynamic surface that you're measuring can create a disturbance in the measurement. We're talking about measuring relatively low pressures, and we're doing that in a highly turbulent, flow disturbed environment.
Okay.
So if we don't do things to mitigate some of those effects, that can have a pronounced, visible effect on the measurement that we're trying to take. Again, circling back to an earlier point, the measuring instrument, largely speaking, is going to do what it's being told to do.
Yeah.
And there's an element there of, it looks like there's a problem with the instrument, but actually it's being derived from something at the measurement surface that we're looking at, and we can help to tune this, the point where we're actually collecting the measurement to the point where we're measuring it. And so it's those kinds of things. Make sure we're paying attention to the whole measuring circuit, not just the instrument that's doing the measurement.
Okay, that makes sense. Because I think when I came to the head office in December last year, you had a whole bunch of calibration stuff set out on the table already, and there were systems going off on that side and products going off on this side. So you are from start to finish, you're measuring the whole unit, and there were quite a few aspects on the table at the time. And obviously, not coming from an engineering background, it was over my head, but it made sense when you could see the data on the screen. And what you're showing me is if you block this and all of a sudden cuts off the kind of the flow, straight away at that end, you could see the data on the computer almost instantly. And obviously the environment that we're in a warehouse, that plays a factor. So it's very interesting to kind of see it in a table in front of you, because otherwise you don't. As engineers, it's a bigger setup, I would think too.
I think it's easy to look at something and not have the full picture about what it's taken to achieve what we're putting in front of people.
Yeah.
Our pressure scanning instruments, for example, are some of the smallest available in the world, and carry a reasonably big price tag. It's not the kind of thing you would buy to put on your mantelpiece at home or something like this. So it can look like it's as a consumer item, it would seem to be carrying or seem to cost a lot of money. What's not seen is the work that goes on in the background to make sure all of those electronic components and the pressure sensors particularly are going to play along nicely when they put them into it, when we're in an environment where we're expecting measurement. Our job is to produce a measuring instrument or a system that's going to start adding value to our client's application the moment they get it in their hands and start getting that detail. When you're in high criticality environments, very important that we start getting good quality, reliable, repeatable measurements very, very quickly. And those are the environments in which we operate. So it's we're being relied upon in order to bring about those conditions and capability.
Definitely. I think the whole quality and accuracy comes with an investment. Like you've got this really important industry that you can't mess around with. So yeah, definitely you're investing in that precision, reliable, quality data that you've just mentioned.
There's nothing trivial about it. It's there are significant consequences that we need to avoid and make sure that we're delivering quality.
The fun question. So I ask this every episode. What did you want to when you grew up?
It's a very good question. First my instinctive response is I still don't know. I'm still trying to figure that out. Not too sure if I've grown up yet. I grew up, Lindsay, taking things apart, generally to other people's frustration, because initially it was not so easy to get things back together.
That was going to be my question. Could you put them back together?
You best not talk to my parents. But I clearly had a persuasion in the direction of engineering, which was somewhat alien to my family. It's not something as a family we've been traditionally involved with. I guess I naturally gravitated towards getting into an engineering environment, and where we are in our business, I guess for me feeds a lot of that. I think I probably would like to have been a racing driver, but I don't have the physical build for it. I don't think I don't necessarily have the reaction speed for it. And when I say that, it's lucky you can only see me from home here. Really. So I know, and I didn't get into the right environments to bring that about early enough. But we're fortunate as a business. We interface with some of the most advanced environments in the world: motorsport, aerospace, all levels of automotive, renewable energies, very high-end metrology, and all of those are things that stoke passion for me. So in a lot of ways I've been fortunate to find something that I can feed that inner burn, if you like. But that's probably as close an approximation as to where did I want to get to. Or what did I want to be?
You're still growing, still learning. There's still loads of time. So following that, actually, have you ever not been able to put something back together?
Oh, more times than I want to count now. It's
you don't want to say that out loud.
but much earlier in life, I have to say. These days I've learned these days I've learned what to not take apart in the first place and put that into the hands of the people that can deal with it. No, I mean, we put together some fairly sophisticated turnkey systems for people that have to do very high criticality, high repeatability tasks, and we're we're very fortunate, we're very honored. We work with some very recognizable big named companies that at a consumer level one would recognize, and we have to supply say high capability technical solutions to people. So yeah, fortunately most of the things that I ever take apart these days go back together and continue to work afterwards
With no super glue.
but with no super glue and no ongoing problems.
That's great. That's what we want to hear. Yes, I think that wraps up our session. I think we've covered a lot in the aerospace and the calibration and the pitfalls. So a really good session. So thank you for being here today, Paul. I've learned a lot, certainly, about what really goes into the calibration industry, and specifically the aerospace industry, because it's even more crucial, I would say. Not that other industries aren't, but it's very, like you said, very scrutinized. So it's definitely a learning curve, being front and center. So yeah, thank you for being here, and I look forward to the next episode. Keep a watchful eye out for the next episode, and we will be in touch. Thank you, Paul.
Pleasure's mine. Thanks, Lindsay.